Close your eyes and imagine holding a human skull in your hands. Not just any skull. This one is older than the pyramids, older than Stonehenge, older than agriculture, older than language as we know it, older than every single thing humans have ever built or written or remembered. This skull is so old that when the person it belonged to was alive, there were entire species of humans walking the earth that don't exist anymore. Species we'll never meet. Species that vanished without leaving a trace except for fragments of bone buried in African soil. Now imagine that this single skull, this one piece of ancient bone, was enough to make scientists throw out their textbooks and start over. Because that's exactly what happened. The discovery we're going to explore tonight changed everything. And I mean everything. It redrew the entire map of human evolution. It pushed our timeline back further than anyone thought possible. It proved that scientists who spent their entire careers studying human origins had been looking in the wrong places, at the wrong times, building theories on foundations that turned out to be completely wrong. If you're settling in to fall asleep, perfect. That's exactly why I make these. So get comfortable, maybe subscribe if you haven't already, and here's the fun part. Comment below and tell me where you are right now and what time it is. I love checking the comments and seeing Tokyo at sunrise, London at lunch, Los Angeles at midnight, all watching the same story unfold across time zones. It's like this community spans the whole planet, which is pretty fitting for a story about human origins. Tonight's journey starts in a place most people have never heard of, a remote excavation site where the temperature reaches scorching highs during the day and the dust gets into everything, your clothes, your equipment, your lungs. It's the kind of place where only the most dedicated researchers spend their time, digging through layers of ancient sediment, hoping to find something, anything, that might tell us where we came from. And then, one day, someone finds it. A skull. Fragments at first, then more pieces, carefully excavated over weeks and months. And as they clean away the dirt and stone that's encased it for nearly 1 million years, they start to realize what they're looking at. This isn't just another fossil. This is something that shouldn't exist. Not here. Not at this age. Not with these features. The moment scientists began analyzing this skull, arguments erupted. Heated debates in academic journals, conferences where researchers literally shouted at each other. Careers were made and destroyed over interpretations of this single find, because accepting what this skull represented meant admitting that the story of human evolution, the story we'd been teaching in universities and museums around the world, was incomplete at best and fundamentally wrong at worst. See, the thing about paleoanthropology, the study of human origins, is that it's like trying to complete a jigsaw puzzle when you only have a handful of pieces and no picture on the box to guide you. Every new fossil is another piece, and sometimes that piece fits exactly where you expected. But sometimes, like with this skull, that piece doesn't fit anywhere in your existing puzzle, and you have to ask yourself, is the piece broken, or is the puzzle wrong? In this case, the puzzle was wrong. This discovery opened doors to questions nobody had even thought to ask. It revealed gaps in our family tree we didn't know existed. It suggested that our ancestors were doing things, living in places, developing abilities, much earlier than we ever imagined possible. And most incredibly, it hinted that there were entire chapters of human history we knew absolutely nothing about. Chapters that might be lost forever. Over the next few hours, as you drift in and out of consciousness, we're going to walk through this story together. From the moment of discovery to the painstaking work of dating the skull using cutting-edge technology. From the shocking revelations about its anatomy to the fierce scientific battles that followed. We'll meet the researchers who staked their reputations on this find, and the skeptics who tried to tear their theories apart. We'll explore what life was like for the person this skull belonged to, 1 million years ago, in a world so different from ours it might as well be an alien planet. And we'll trace the line from that ancient individual to you, lying here tonight, listening to this story. Because here's the beautiful thing about this discovery. It's not just about the past, it's about us. Every revelation about our ancestors is a revelation about ourselves. Every mystery they solved is a clue to understanding why we are the way we are. So let's begin. Let's go back to a time before history, before memory, before anything recognizable as human civilization. Back to the moment when everything we thought we knew about ourselves was about to change forever. The story starts with a hole in the ground and a fragment of bone that refused to make sense. Picture a university lecture hall in 1920. Dark wood panelling, rows of young men in suits, no women, because most universities wouldn't admit them to anthropology programs. At the front, a professor gestures at a chart showing human evolution as a neat straight line from ape to European gentleman. Simple, clean, completely wrong. But they didn't know that yet. The world of early 20th century anthropology was tiny, insular, and almost entirely European. A handful of scholars, mostly men from wealthy families who could afford to spend years studying dusty bones, debating the origins of humanity over brandy in London clubs and Parisian cafes. They had impressive credentials, elaborate theories, and almost no actual evidence. Think about that for a moment. These were the men trying to reconstruct millions of years of human evolution. They were working with fewer complete ancient human fossils than you could count on both hands. Some of the most prominent anthropologists had never even seen an original fossil, only plaster casts and drawings. Yet they spoke with absolute certainty about how, when, and where humans evolved. Their certainty wasn't based on evidence, it was based on assumptions. Assumptions that reflected the prejudices and blind spots of their era. And those assumptions shaped everything they believed about human origins. The dominant theory was straightforward. Humans evolved recently, probably within the last few 100,000 years. And they evolved in Europe or possibly Asia, anywhere but Africa. The idea that humanity's origins lay in the Dark Continent was considered by many European scholars to be not just unlikely, but almost offensive. After all, Europe was the centre of civilization, the pinnacle of human achievement. Surely, they reasoned, it must also be humanity's birthplace. This wasn't just cultural bias. It was scientific racism dressed up in academic language. Many early anthropologists openly ranked human races in hierarchical orders, with Europeans at the top and Africans at the bottom. They interpreted every fossil discovery through this lens. Anything that suggested greater complexity or intelligence was automatically assumed to be more closely related to Europeans. Anything that seemed more primitive was pushed toward the African side of the family tree. The sparse fossil record made it easy to maintain these biases. In 1920, the entire collection of ancient human remains consisted of maybe a dozen significant finds scattered across museums in Europe and Asia. Each discovery was treated like a sacred relic. Scholars built entire theories around single teeth, fragments of jaw, pieces of skull so small you could hold them in your palm. The most famous find was Neanderthal man, discovered in Germany's Neander Valley back in 1856. For decades, scientists argued about what it meant. Was it a separate species? A diseased modern human? An evolutionary dead end? Nobody could agree. The original bones were passed from researcher to researcher, each one proposing a different interpretation, each one convinced they alone understood the truth. Then came Java man, discovered by a Dutch anatomist named Eugene Dubois on the Indonesian island of Java in the 1890s. Just a skull cap and a thigh bone found yards apart, not even definitely from the same individual. But Dubois declared it the missing link between apes and humans. He named it Pithecanthropus erectus, upright ape man. Other scientists weren't convinced. Some thought it was just a large gibbon. Others argued it was a modern human with unusual features. The debates raged for decades. This was the state of paleoanthropology. Fragmentary bones, endless arguments, and very little consensus. But underlying all the debates was one central obsession: the missing link. Darwin's theory of evolution had been around since 1859, but it left a crucial question unanswered. If humans and apes shared a common ancestor, where was the fossil evidence of the transition? Where were the creatures that were more than apes, but less than human? The intermediary forms that should connect us to our primate cousins. Scientists were desperate to find these missing links, not just to prove evolution, though that was part of it. More than that, finding the missing link would mean fame, recognition, a place in history. Museums and wealthy patrons offered funding for fossil hunting expeditions. Academic careers were made or destroyed based on the significance of your discoveries. This created a problem. When you're looking for something specific, when your reputation and funding depend on finding it, you start seeing it everywhere. Ambiguous fossils got interpreted as missing links. Fragmentary remains got reconstructed to fit expectations. In the worst cases, researchers saw what they wanted to see instead of what was actually there. The most spectacular example was Piltdown Man. Discovered in England in 1912, it consisted of a human-like skull and an ape-like jaw. British scientists hailed it as the ultimate missing link, proof that humans had evolved in England itself. Charles Dawson, the amateur archaeologist who found it, became famous overnight. Museums created elaborate reconstructions. Textbooks featured it prominently. There was just one problem. It was a hoax. Someone had taken a medieval human skull and an orangutan jaw, filed down the teeth to look more human, and stained everything to appear ancient. But British scientists wanted to believe they'd found evidence of English evolutionary superiority so badly that they didn't question it carefully enough. The fraud wasn't exposed until 1953, more than 40 years later. By then, Piltdown had misled an entire generation of researchers, but even legitimate fossils were interpreted through deeply flawed frameworks. Early anthropologists assumed that brain size was the most important marker of human evolution. Bigger brains meant more advanced, more human. This seemed logical. Modern humans have large brains compared to apes, so surely the first thing that made our ancestors human was brain expansion. This led to a predicted sequence. First came the big brain, then upright walking, then tool use. Brain first, everything else followed. It made intuitive sense to scholars who valued intelligence above all else. The brain, the seat of reason and thought, must have been the key adaptation that separated humans from animals. Based on this assumption, scientists made predictions about what the missing link should look like. Something with a large, human-like skull but ape-like body. A creature that had evolved intelligence first but retained the physical characteristics of its primate ancestors. This was exactly what Piltdown Man appeared to show, which is one reason so many experts accepted it so readily. They were also convinced that human evolution had been relatively recent and relatively fast. A few 100,000 years, maybe 500,000 at most, from ape-like ancestor to modern human. Deep time, the vast stretches of geological history that Darwin had invoked, didn't seem necessary for human evolution. We were special, different, separate from the slow grinding processes that shaped other species. This created a very specific picture of human prehistory. Somewhere in Europe or Asia, within the last 500,000 years, an ape-like creature had suddenly developed a larger brain. This mental leap forward had set it on the path to humanity. It learned to walk upright, make tools, develop culture. Within a relatively brief period, it transformed from animal to human. It was a comforting story. It made humans exceptional, our evolution rapid and dramatic, our superiority self-evident. It placed our origins in familiar, civilized landscapes rather than the mysterious depths of Africa. And it required very little time, very little evidence, very little complication. But it was wrong, almost entirely wrong. The problem was that early anthropologists were trying to reconstruct millions of years of evolutionary history from a handful of broken bones. It's like trying to understand an entire novel by reading 3 random words from different pages. You might construct a story, but it's going to be your story, not the author's. Your biases, assumptions and expectations will fill in all the gaps, and the gaps were enormous. Between the few known fossils stretched vast chasms of time, hundreds of thousands of years with no evidence at all. Different species might have risen and fallen. Entire branches of the human family tree might have flourished and gone extinct, and nobody would know because the fossil record was so incomplete. Some scientists recognized this. They urged caution, argued for gathering more evidence before making sweeping conclusions. But they were drowned out by the confident voices of the establishment, the prominent professors and museum directors who spoke with certainty because their positions demanded it. There was also a geographical problem. Nearly all fossil hunting happened in Europe and Asia. A few expeditions had ventured into Africa, but they were poorly funded, often dismissed as unlikely to yield important discoveries. Why waste resources searching the African wilderness when the real story of human evolution was obviously playing out in the civilized world? This created a massive sampling bias. Scientists were looking for human ancestors in Europe and Asia, so naturally that's where they found them. Every European fossil was celebrated as a crucial piece of the puzzle. Asian discoveries were studied intensively. African finds, when they happened at all, were often treated as curiosities, interesting but peripheral to the main story. Meanwhile, dating techniques were primitive at best. Researchers estimated the age of fossils based on the geological layers where they were found, but those estimates could be off by hundreds of thousands of years. Without accurate dates, it was impossible to know which fossils were older, which represented ancestors and which descendants, which were direct human ancestors and which were evolutionary dead ends. So the field existed in a strange state. Lots of theory, lots of confident pronouncements, but very little solid ground beneath it all. The foundation was built on sand, assumptions stacked on assumptions, interpretations piled on interpretations, all supported by a tiny collection of fragmentary bones. But cracks were starting to appear in the consensus. A few researchers were beginning to question the European origin story. A few fossils were turning up that didn't fit the expected pattern. Brain size wasn't always increasing in a neat progression. Some ancient humans had surprisingly small brains but sophisticated tools. Others had large brains but seemed to lack cultural complexity. The neat straight line from ape to human was getting messier. Maybe human evolution wasn't a ladder but a branching bush. Maybe multiple human species had coexisted. Maybe the timeline was longer, the geography more complex, the story more complicated than anyone had imagined. The scientific community in the early 20th century was like a powder keg. The old theories were showing their age. The sparse evidence was being stretched beyond its limits. The assumptions and biases that had shaped the field for generations were increasingly difficult to maintain. All it would take was one discovery, one fossil that couldn't be explained away, dismissed, or forced into the existing framework. One find that demanded a complete rethinking of human origins. The stage was set. The actors were in place. The old guard clinging to their theories, the young rebels pushing for change, the patient bones waiting in the earth to tell their story. Somewhere in Africa, buried in ancient sediments, lay a skull that would shatter everything they thought they knew. Nobody was ready for what was coming. Nobody could have been. Because the truth about human origins was far stranger, far older, and far more African than anyone in those European lecture halls could have possibly imagined. The revolution was about to begin. Picture the East African Rift Valley in the early morning, sometime in the early 20th century. The sun hasn't quite risen yet, but the sky's already bleeding orange and gold across the horizon. The air is cool, almost cold, which is a mercy because in a few hours it'll be pushing 95 degrees in the shade. Except there isn't much shade, just endless stretches of eroded badlands. gullies carved by seasonal rivers that only flow a few weeks a year, and exposed rock faces where millions of years of geological history lie open like the pages of a book. This is where the impossible would be found, not in some dramatic Indiana Jones moment with temples and treasure, but in the dust and heat and back-breaking tedium of systematic fossil hunting. The landscape itself is otherworldly. Volcanic ash layers alternate with ancient lake beds, creating a striped effect in the cliff faces. The ground is littered with stone fragments, most of them just rocks, but some of them tools made by human hands hundreds of thousands of years ago. Fossils weather out of these sediments constantly, exposed by wind and rain, bleaching white in the sun. Most of them are worthless scientifically, fragments too small or damaged to identify, but somewhere in all that geological chaos, complete skulls are waiting. Complete enough to tell stories, old enough to rewrite history. The fossil hunters who worked these sites weren't wealthy academics on safari. They were a different breed entirely. Men and women who had become obsessed with the deep past, who were willing to spend months at a time in brutal conditions for the chance, just the chance, of finding something significant. They worked with minimal funding, inadequate equipment, and the constant awareness that they might spend years searching and find nothing. But they kept searching anyway, because they understood something profound. Every fossil, no matter how fragmentary, is a message from the past, a data point in the grandest story ever told, the story of where we came from and how we became human. Enter the key figures. The discoverer, whose name would eventually be linked forever with this find, wasn't initially looking for human fossils at all. They were part of a broader paleontological expedition, cataloguing the incredible diversity of extinct animals that once roamed these African plains. Giant pigs the size of rhinos, saber-toothed cats, bizarre elephants with 4 tusks. The expedition was documenting an entire lost ecosystem, trying to understand how climate change over millions of years had transformed Africa from dense forest to open savanna. But this researcher had a theory. If the environment had changed so dramatically, and if all these animal species had evolved in response to those changes, then surely the same pressures had shaped human evolution too. Early hominins hadn't evolved in isolation. They were part of this ecosystem, competing with these predators, hunting these prey animals, adapting to the same climate shifts. Find the right geological layers, the right time period, and you'd find evidence of human ancestors responding to environmental pressures in real time. So while the main expedition focused on the spectacular megafauna, our discoverer began paying attention to different geological horizons, looking for layers that dated to periods when the climate was changing rapidly, when forests were giving way to grasslands, when ancient lakes were drying up. These transition periods, they reasoned, would be where evolution was most active, where selection pressure was most intense, where you'd find the most interesting human fossils. It was systematic, methodical work. Walk the erosion gullies slowly, eyes scanning the ground. Mark any promising fragments with small flags for later collection. Map everything meticulously so you can trace fossils back to their original geological context. Because context is everything in paleontology. A skull without context is just a curiosity. But a skull from a precisely dated geological layer tells you when that individual lived, what the climate was like, what other species were present. It transforms bone into history. Day after day, week after week, the same routine. Walking the Badlands in the early morning before the heat became unbearable. Cataloguing finds, mostly fragments of extinct animals, mapping geological formations, then collapsing in the shade during the hottest part of the day, drinking warm water from canvas bags, planning the next day's search pattern. And then one morning, everything changed. The discoverer was working a particular gully that had been exposing interesting fossils. Ancient stone tools had turned up there, suggesting hominins had lived nearby. The geological layer was promising too. dating to a period around 800,000 to 900,000 years ago, right in the middle of the major climate transition they were interested in. The sun was still low, creating long shadows that made small variations in the ground surface more visible. And there, partially exposed in the side of the gully, weathering out of a layer of volcanic ash, was something round. Something the right size. Something that made their heart start pounding even before their conscious mind registered what they were seeing. They approached slowly. In paleontology, excitement is tempered by caution. Most promising finds turn out to be nothing, unusually round rocks, badly preserved fossils of common animals. You learn not to get your hopes up until you've examined something carefully. But as they got closer, the details became clear. The curve of the bone, the thickness and texture, the distinctive features that mark a skull as belonging to the hominin family tree. This wasn't a rock. This wasn't an animal. This was one of our ancestors, lying in the dirt after nearly 1 million years. The discoverer's first action was exactly right. They didn't touch it. They didn't try to excavate it themselves. They sat down right there in the dirt, pulled out their field notebook, and began documenting everything. The precise location, the geological context, the angle at which the skull was positioned, the other fossils visible nearby. They sketched what they could see, took measurements, made notes about the sediment colour and texture. Then they carefully, very carefully, began to excavate around the skull. Not to remove it, not yet, but to expose more of it, to see what they were dealing with, to determine if the skull was complete or just a fragment. Each brushstroke revealed more. The frontal bone, remarkably intact. The eye orbits clearly visible, the beginning of the jaw still attached. This wasn't a fragment. This was a complete skull. Maybe not perfect. There would surely be cracks and missing pieces, but complete enough to study. Complete enough to reconstruct what this individual had looked like. Complete enough to tell them stories about human evolution that no one had heard before. The mixture of emotions in that moment must have been overwhelming. Scientific excitement, absolutely. This was the find of a lifetime, career-defining, the kind of discovery that gets written up in every textbook, but also something deeper, something almost spiritual. This skull had belonged to a living, breathing person. Someone who had been born, grown up, faced challenges, maybe had children, eventually died. Someone who had thoughts and feelings and experiences. And now, after nearly 1 million years, another human was seeing their face for the first time. The discoverer later described feeling a profound sense of connection. Not some mystical nonsense, but genuine recognition. This ancient person was different from modern humans in many ways, but also fundamentally the same. They had walked the same landscape, felt the same sun, probably looked up at the same stars and wondered what they were. But there was no time for philosophical reflection yet. The skull was exposed to the elements. Rain could damage it, animals could disturb it. Hell, another fossil hunter could potentially stumble across it. It needed to be protected immediately and excavated properly. The discoverer marked the spot with multiple reference points, took photographs from every angle, then hiked back to the expedition camp to get help. They needed plaster for making a protective jacket around the skull. They needed the expedition leader and the other senior researchers to witness and verify the discovery. They needed documentation, proper excavation tools, everything required to do this right. The next few days were intense. The entire expedition shifted focus to this single find. They constructed a shelter over the excavation site to protect it from sun and potential rain. They set up a grid system for precise mapping. They brought in all their photographic equipment, still primitive by modern standards, but the best available at the time. Then began the painstaking work of fully exposing the skull. Not just the visible parts, but checking if any other skeletal elements were present. Sometimes you find isolated skulls. Sometimes you find complete skeletons. You never know until you excavate carefully and completely. They worked slowly, using fine tools, dental picks, brushes, sometimes just blowing away sediment breath by breath. Each tiny fragment of bone was noted, photographed, and left in place. They were creating a complete record of the skull's position and context before they removed it. As they worked, the skull's features became clearer. The heavy brow ridges, the robust bone structure, the distinctive shape that wasn't quite modern human but wasn't like any ape either. This was something intermediate, something that documented a crucial stage in human evolution. The initial examinations, even before the skull was removed from the ground, revealed features that didn't fit existing theories. The brain case was larger than expected for something this old. The teeth were more human-like than anticipated. The overall shape suggested a level of sophistication that challenged the prevailing wisdom about when and how humans evolved. The researchers looked at each other with a mixture of excitement and concern. Excitement because this was clearly important. Concern because important discoveries attract scrutiny. Every detail would be questioned, every interpretation challenged. They needed to be absolutely certain of their facts before they made any public statements. After 3 days of careful excavation, they were ready to remove the skull. They had documented everything, photographed from every angle, mapped its position precisely, collected samples of the surrounding sediment for later geological analysis. Now came the most nerve-wracking part, actually lifting the fossil and transporting it to safety. They used the traditional paleontological technique of jacketing. They covered the exposed skull with wet tissue paper to protect the surface. Then they applied plaster-soaked burlap in layers, creating a hard protective shell around the fossil. Once the jacket was complete and dry, they carefully undercut beneath the skull, separating it from the sediment below while keeping everything stable inside the plaster cocoon. The jacketed skull weighed nearly 40 pounds. Bone plus rock plus plaster, all of it precious and irreplaceable. They carried it out of the gully like it was made of glass, walking slowly, trading off when arms got tired. Back at camp, they built a wooden crate padded with straw and carefully nested the jacketed skull inside. Then came the journey, getting the skull from a remote excavation site in East Africa to a proper laboratory where it could be studied. This wasn't like shipping a package today. There were no reliable roads, no air freight, just long overland journeys by truck and train, then eventually by ship with the skull's handlers constantly worrying about damage from jolts and vibrations and temperature changes. The discoverer accompanied the skull personally. They weren't taking any chances. At border crossings, they had to explain repeatedly what they were transporting and why it was important. Some officials were fascinated, others were suspicious. One border guard apparently suggested they were smuggling drugs inside the plaster jacket and wanted to break it open to check. It took hours of negotiation and documentation to prevent that disaster. But eventually, after weeks of careful transport, the skull arrived at a major research institution, still in its plaster jacket, still protected, ready to reveal its secrets to a new generation of scientists who would spend years studying every millimetre of its surface. The skull had survived nearly 1 million years buried in African sediments. It had survived exposure and excavation. It had survived a journey across continents. Now it would survive something else entirely. The intense scrutiny of the scientific community, the debates and arguments about what it meant, the challenge it posed to everything people thought they knew about human evolution. Because this skull was impossible. It was too old to have the features it displayed, too advanced for its time period, too complete to be dismissed as an oddity or an outlier. This skull was about to change everything. But first, scientists had to figure out exactly how old it was, and that would prove to be its own kind of challenge. Here's the problem with finding something impossibly old. How do you prove it? When that skull emerged from the ground, holding it was one thing. Understanding what you were actually holding, that was something else entirely. Because in those early days, Scientists had no reliable way to determine exactly how old ancient bones were. They could make educated guesses. They could compare the fossilization state to other specimens. They could look at the rock layers surrounding the discovery, but precision, certainty, that was asking the impossible, and yet this skull demanded an answer. Its morphology suggested extreme antiquity. The fossilization was unlike anything most researchers had seen. The skull wasn't just old, it was ancient in a way that challenged every assumption about how far back the human lineage extended. But without a reliable method to date it, skeptics could dismiss it. They could claim it was younger than it looked, that the fossilization process had been unusually rapid, that the finders had made mistakes about which layer of rock it came from. So began one of the most important scientific detective stories in human history. A century-long quest to answer a single question. Exactly how old is this thing? The first approach was stratigraphy, basic geological layering. This principle is beautifully simple. Newer rock layers form on top of older ones. If you find a fossil deep in the ground below multiple layers of sediment, it has to be older than everything above it. The researchers who discovered the skull carefully documented exactly where it came from. They noted the specific geological layer. They mapped the surrounding stratigraphy. They took samples of the sediment and rock formations. What they found was both encouraging and terrifying. The skull came from a layer that was demonstrably ancient. Below it were deposits that had been dated to the early Pleistocene era. Above it were layers that took hundreds of thousands of years to form. The stratigraphic evidence suggested the skull was at least 800,000 years old, possibly much older. This was astronomical compared to what most scientists believed about human evolution at the time. But stratigraphy alone wasn't enough. Too many variables. Geological disturbances could move fossils up or down through layers. Water erosion could relocate remains. Earthquakes and tectonic activity could jumble everything together. The skeptics weren't convinced, and honestly they had good reasons to doubt. So the researchers turned to a second method: associated fauna. The animals you die with tell a story about when you lived. When the skull was discovered, it wasn't alone. The same geological layer contained fossils of extinct animals. Ancient elephants that hadn't walked the earth for nearly 1 million years. Saber-toothed cats that had vanished long before recorded history. Rodents and bird species that modern paleontologists could identify and date based on their evolutionary stage. This was powerful evidence. You can't just appear next to animals that went extinct 900,000 years ago. The associated fauna created a temporal fingerprint, a snapshot of what the ancient ecosystem looked like. When paleontologists analysed these animal remains, the story became clearer. The fauna assemblage matched other sites that had been dated to the early Pleistocene. The specific evolutionary stages of the species present all pointed to the same narrow window of time. The skull was old, really old, somewhere between 800,000 and 1 million years ancient. The scientific community exploded. Half of them were fascinated, energized by the implications. The other half were deeply skeptical. Because accepting these dates meant rewriting the entire timeline of human evolution. It meant our lineage was far older, far more complex than anyone had imagined. It meant throwing out decades of carefully constructed theories and starting over. The debates were fierce. Conferences turned into battlegrounds. Respected scientists who had spent their entire careers building evolutionary models suddenly found their life's work challenged by a single fossil. Some refused to accept the dates outright. They argued the stratigraphy had been misread. They claimed the associated fauna had been contaminated, mixed with the skull's layer through geological processes. They demanded more evidence, better evidence, unimpeachable evidence, and then the technology evolved. By the mid-20th century, scientists had developed radiometric dating techniques. These methods were revolutionary because they didn't rely on context or comparison. They measured the actual decay of radioactive elements within the fossils and surrounding rock. When an organism dies, radioactive isotopes in its body begin breaking down at a known constant rate. By measuring how much decay has occurred, scientists can calculate exactly how long ago death happened. The problem was, most radiometric dating methods didn't work well on fossils this old. Carbon-14 dating, the most famous technique, only works on remains younger than about 50,000 years. After that, too little carbon-14 remains to measure accurately. For the skull, carbon dating was useless. The specimen was far too ancient. But there were other methods. Potassium-argon dating measures the decay of radioactive potassium into argon gas in volcanic rock. If the skull was found near volcanic deposits, those deposits could be dated with incredible precision. Uranium-lead dating measures the decay of uranium isotopes in minerals. Electron spin resonance dating measures radiation damage in tooth enamel and bone. When these techniques were finally applied to the skull's site, something remarkable happened. The dates started converging. Different methods, measuring different isotopes, using completely independent physical processes, all pointed to the same time frame. The volcanic ash layer just above the skull, 900,000 years old. The mineral deposits in the surrounding rock, 950,000 years old. The radiation damage in nearby mammal teeth, consistent with roughly 1 million years of exposure. The skeptics had demanded unimpeachable evidence. Now they had it. From multiple independent sources using cutting-edge technology, all pointing to the same inescapable conclusion. This skull was approximately 1 million years old, give or take 100,000 years, which in geological terms is basically nothing. But here's where it gets wild. What does 1 million years actually mean? Think about this. Recorded human history goes back maybe 5,000 years. That's everything. All the civilizations you've ever heard of. Ancient Egypt, Mesopotamia, Greece, Rome, China. All of it fits within the last 5 millennia. Now multiply that by 200. That's 1 million years. If you tried to count to 1 million, counting one number per second without stopping, it would take you 11.5 days. If you tried to walk back through time at the rate of 1 year per step, you'd need to take 1 million steps to reach when this individual died. At an average walking pace, that would require walking continuously for about 3 weeks. The human mind simply isn't equipped to comprehend these timescales. Evolution operates on a temporal canvas so vast that our brains, adapted for thinking about days and seasons and lifetimes, struggle to grasp it. 1 million years isn't just old, it's ancient beyond our intuitive capacity to understand. And yet, in the grand timeline of Earth's history, 1 million years is recent. The planet is 4.6 billion years old. Life has existed for at least 3.5 billion years. Complex multicellular animals have been around for over 500 million years. In that context, 1 million years is like the last few minutes of a 24-hour day. But for human evolution, 1 million years is transformative, absolutely foundational. When scientists began comparing the skull to other dated human fossils, patterns emerged. There were other specimens from roughly the same period, some from Africa, some from Asia, a few from Europe. What became clear was that 1 million years ago, multiple human species existed simultaneously. They were spread across 3 continents. They looked different from each other, adapted to different environments, but they were all recognizably human in ways that earlier species weren't. This skull fit perfectly into that merging picture. Its anatomy showed features that were intermediate between older, more primitive species and later, more modern ones. Its age placed it right at a crucial branch point in human evolution. This wasn't just another fossil. This was evidence of a pivotal moment when our lineage was diverging, adapting, becoming the varied collection of human species that would eventually spread across the entire planet. But even as the dating became more precise and more accepted, controversy continued. Some scientists argued that even if the dates were accurate, the skull might not represent a direct ancestor of modern humans. It could be a side branch, an evolutionary dead end, a cousin rather than a grandparent. Others suggested that the skull's unusual features meant it should be classified as a separate species entirely, not part of the human lineage at all. These debates continued for decades. Even today, aspects of the skull's classification remain contentious. But what's no longer debatable is its age. Modern dating techniques, applied multiple times by independent research teams, have consistently confirmed the initial estimates. This skull is approximately 1 million years old. That's not speculation anymore. That's established fact, confirmed by geology, paleontology, and radiometric dating. What changed wasn't the skull. The skull has always been exactly as old as it is. What changed was our ability to read the clues preserved in rock and bone. Every advancement in dating technology brought new precision, new confidence, new understanding. By the late 20th century, scientists had developed even more sophisticated methods. Argon-argon dating refined the potassium-argon technique, reducing error margins. Paleomagnetic dating measured the reversal of Earth's magnetic field recorded in rock layers. Cosmogenic nuclide dating measured isotopes created by cosmic ray bombardment. Each method added another piece to the puzzle, another confirmation of the skull's impossible antiquity. The result is that today we can date this skull with precision that would have seemed like science fiction a century ago. We know not just that it's roughly 1 million years old, but which specific climatic period it lived during. We can correlate its existence with ancient volcanic eruptions, climate shifts, and evolutionary events in other species. We can place this individual's death within a 10,000-year window in a 1 million-year timeline. That's the power of modern science. The ability to take a fragment of bone and extract from it a precise date, a specific moment in deep time. The ability to look at a skull and say with confidence, this individual died approximately 950,000 years ago, give or take 50,000 years, during a period of severe climate fluctuation in a landscape that no longer exists, among species that have long since vanished. And with that date established, with that temporal anchor firmly in place, scientists could finally begin asking the really interesting questions. Not just how old is this skull, but what does its age tell us? What was the world like 1 million years ago? What challenges did this individual face? How did their species survive in conditions that would kill modern humans in days? The dating of the skull didn't end the story. It opened the door to understanding a world separated from ours by an almost incomprehensible gulf of time. A world where humans existed, but barely. Where survival meant something completely different than it does today. Where every day was a battle against extinction, and every generation that survived was a small miracle. That's what 1 million years old really means. It means this skull is a message from a world so ancient, so alien, that it might as well be from another planet. And yet, it's from here, from Earth, from our ancestors, from the people whose survival made our existence possible. The dates don't just tell us when. They tell us how far we've come, how much we've changed, and how incredibly unlikely it is that we're here at all. Now let's talk about the skull itself. Because this wasn't just some pile of bone fragments. This was a window into a world that no human had seen for 1 million years. When the researchers finally got the skull into the laboratory, cleaned, reconstructed, and ready for analysis, they were looking at something that shouldn't exist. At least not according to everything they thought they knew about human evolution. The first thing that grabbed their attention was the cranial capacity, the brain size. They measured it 3 times, thinking they'd made a mistake, because the number they kept getting was impossible. 900 cubic centimetres, maybe pushing toward 950 in life, accounting for the usual compression that happens to fossils over time. To put that in perspective, modern human brains average about 1,350 cubic centimetres. Chimpanzees, our closest living relatives, have brains around 400 cubic centimeters. This skull was sitting right in the middle, not quite human, not remotely ape, but something profoundly in between. But here's what made it revolutionary. At 1,000,000 years old, this individual had a brain significantly larger than anything else from that time period. The other fossils from this era showed brain sizes around 750 to 800 cubic centimeters. This skull represented a massive leap forward, a 20% increase in brain volume. That's not just evolutionary drift, that's selection pressure, that's evolution pushing hard in a specific direction. The skull was telling a story about intelligence under pressure, about minds growing larger because they had to, because the world was becoming more challenging, and only the smartest, most adaptable individuals were surviving long enough to reproduce. But brain size is just one piece of the puzzle. The real insights came from examining the shape of the skull, the architecture of this ancient face. The face itself was remarkable, projecting forward more than a modern human's, but nothing like the pronounced snouts of earlier hominins. The cheekbones were massive, flaring out from the skull like buttresses. These weren't just for show. Those robust cheekbones were attachment points for enormous jaw muscles. This individual could bite down with crushing force. The teeth told the same story. Molars worn nearly flat from years of grinding. Not just soft fruits and occasional meat, but tough, fibrous plant materials. Roots pulled from hard ground. Seeds that needed serious processing. This was someone who ate whatever they could find and had the dental equipment to make it work. The jaw was thick, heavily built, with attachment points showing muscle development that would be exceptional even in modern athletes. This person chewed for hours every day. Food processing wasn't something you did quickly and moved on. It was a major investment of time and energy. But here's where it gets interesting. The wear patterns on the teeth weren't random. They showed evidence of tool use. Microscopic scratches running at specific angles, exactly what you'd expect from someone who regularly held plant fibers or animal materials in their teeth while cutting them with stone tools. This wasn't just eating, this was food processing, planning, using tools not just occasionally, but as a regular part of daily survival. The eye sockets were large, positioned forward in the skull for excellent depth perception. This was someone who needed to judge distances accurately, maybe for throwing, maybe for navigating complex terrain, definitely for hunting or avoiding being hunted. The brow ridge was prominent, a thick shelf of bone protecting the eyes. Modern humans have almost lost this feature, but in this skull it was pronounced. Not as extreme as in earlier hominins, but definitely there. This suggests a lifestyle that involved physical conflict, environmental hazards, the kind of existence where protecting your eyes and brain from impact trauma was worth the metabolic cost of building extra bone. But the really fascinating details were inside the skull. When the researchers made detailed scans and created 3D models of the internal surface, they could see the impressions left by the brain itself. The pattern of blood vessels, the shape of different brain regions, all preserved like a fossil memory of thoughts long vanished. The frontal lobe showed significant expansion. These are the regions associated with planning, decision-making, impulse control, and social behavior. This individual had a brain that was developing the capacity for complex thought. Not modern human-level cognition, not yet, but moving decisively in that direction. The language centers showed interesting development too. Not fully modern, but more developed than in earlier hominins. Whether this individual could actually speak in anything like human language, we'll never know. But they had the neural architecture that was starting to make language possible. They could probably communicate in ways far more sophisticated than any other animal on Earth at that time. The visual processing areas were enlarged, consistent with those forward-facing eyes and that need for accurate depth perception. This was someone who lived in a world where seeing clearly, judging distances accurately, and processing visual information quickly could mean the difference between eating and being eaten. When scientists compared this skull to modern humans, the differences were striking but not overwhelming. Side by side, you could see the family resemblance. The basic architecture was similar. The proportions weren't wildly different. Put some flesh on this ancient skull, and you'd recognize it as human. Not quite modern, but unmistakably our family. The similarities were actually more surprising than the differences. The rounded skull shape, already moving away from the elongated forms of earlier hominins. The relatively small face compared to the brain case. The teeth that were still large by our standards, but tiny compared to earlier ancestors. This was a creature that was already most of the way toward becoming us. But compare this skull to other hominins from around the same time period, and it stood out dramatically. Specimens from Africa showed smaller brains, more pronounced facial features, less evidence of the kind of complex tool use that these wear patterns suggested. This individual represented a population that was evolving differently, facing different challenges, developing different solutions. Some researchers think this represents a northern population, groups that had pushed into harsher environments and were adapting to more challenging conditions. The robust facial features, the heavy jaw, the enlarged brain, all consistent with populations facing seasonal food, scarcity and environmental stress. The skull showed other signs of adaptation too. The sinus cavities were large and complex, suggesting this individual lived in a cold or dry climate where air needed to be warmed and humidified before reaching the lungs. The blood vessel patterns showed adaptations for maintaining brain temperature in variable conditions. This wasn't someone living in a stable tropical environment. This was someone dealing with real climate stress. The base of the skull showed muscle, attachment points indicating a body built for endurance rather than raw power. Long, efficient muscles designed for walking long distances, not sprinting or climbing. This was a terrestrial hominin, someone who lived on the ground and covered serious territory in their daily life. But perhaps the most poignant details were the ones that told us about this individual's actual life. Not just their species or their adaptations, but their personal story. The skull belonged to an adult, probably somewhere between 30 and 40 years old at death. That's middle-aged by their standards, possibly even elderly. They'd survived long enough to accumulate significant tooth wear, to develop arthritic changes in their jaw joints, to show evidence of healed injuries and recovered infections. Life had been hard for them. The skull showed healed fractures on the left side, probably from a fall or a blow years before death. They'd survived it. That alone tells us something important. They'd had a community. Someone had cared for them during recovery. You don't heal from a serious head injury alone in the wilderness. Sex determination from skulls is always uncertain, but the robust features and large size suggested male, though not definitively. Whether man or woman, they'd been a survivor. Someone who'd made it through droughts, famines, predator encounters, and intergroup conflicts to reach an age where most of their contemporaries were already dead. The cause of death remains mysterious. There's no obvious fatal injury to the skull. They might have died from disease, from an injury to another part of their body, from simple old age. At 1,000,000 years past, those details are lost forever. But the skull also showed something else. Evidence of dental infection that had been ongoing for years before death. A chronic abscess that would have caused constant pain. They'd lived with it, adapted to it, continued functioning despite discomfort that would send modern people straight to a hospital. This speaks to remarkable toughness, but it also speaks to something else. They'd survived with a chronic condition because their community supported them. They had value beyond their physical perfection. Maybe they were a skilled tool maker. Maybe they were a knowledge keeper, someone who remembered where water could be found during droughts, which plants were edible and which were poisonous. Maybe they were simply loved, cared for because their group recognized them as kin. That might be the most profound revelation of all. This skull, this 1,000,000-year-old skull, shows us that the qualities we think of as essentially human, caring for the sick, valuing individuals beyond their immediate utility, maintaining social bonds across years and decades. These weren't late developments. They were already present 1 million years ago in people who weren't even our direct ancestors. The skull revealed something else too, something the researchers didn't fully understand, until they started looking at the genetic data from other fossils. This individual represented a population that was part of the great bottleneck story. Their slightly reduced genetic diversity, their adaptations to environmental stress, their enhanced brain development, all consistent with a population being refined by intense selection pressure. They were living through the early stages of the crisis. Not the worst part. That was still thousands of years in their future, but the beginning. The time when climate was becoming unstable, when resources were starting to become unpredictable, when only the smartest, most adaptable, most cooperative groups could survive. This skull was a snapshot of human evolution at a critical moment. The moment when we were being forged into something new, something capable of surviving the unsurvivable, something that would eventually give rise to 3 human species, all bearing the marks of this crisis in their genes and their bones. Looking at this skull in the laboratory, researchers were seeing their own deep ancestor. Not directly, the exact lineage is more complicated than that, but fundamentally. This was the kind of individual whose descendants would survive the bottleneck, would spread across continents, would eventually become us. Every feature, from the enlarged brain to the worn teeth to the healed fractures, told the same story. Survival through intelligence, through adaptation, through community and cooperation, through sheer, stubborn refusal to let harsh conditions win. We carry their legacy in every cell. Their genes survived 1 million years of climate disasters, population crashes, and evolutionary bottlenecks to reach us. When we solve problems, when we care for our sick, when we work together to overcome challenges, we're using abilities that were being refined in brains like this one 1 million years ago. The skull was just bone. But it revealed something profound about what it means to be human, and what our ancestors endured to give us that humanity. The skull sat in a laboratory in Tbilisi, Georgia. Just a piece of fossilized bone, really. But it might as well have been a bomb waiting to detonate in the middle of the scientific establishment. Because when the full analysis came back, when the dating was confirmed, when every possible alternative explanation had been exhausted, the paleontology community had to face an uncomfortable truth. Everything they thought they knew about human evolution, at least half of it was wrong, not slightly incorrect, not in need of minor revisions, fundamentally, catastrophically wrong. The first theory to collapse was the most basic one, where humans evolved. For decades, the consensus had been clear, clean, almost elegant in its simplicity. Early hominins originated in East Africa, specifically the Great Rift Valley. They evolved there for millions of years, gradually becoming more human-like. Then, around 1 million years ago, maybe 800,000 at the earliest, the first members of genus Homo left Africa and began spreading into Europe and Asia. It was called the Out of Africa theory. And it wasn't just some fringe hypothesis, it was foundational, the framework that organized everything else scientists understood about human origins. University textbooks taught it, museum exhibitions illustrated it, grant proposals referenced it as established fact. Then this skull showed up, sitting in sediment in the Caucasus Mountains, dated to 1.8 million years ago. Not 800,000, not even close. More than twice as old as humans were supposed to be outside Africa. The implications rippled outward like cracks spreading across ice. If humans had reached Georgia 1.8 million years ago, they had left Africa far earlier than anyone imagined, probably closer to 2 million years ago, maybe even earlier. The entire timeline had to be redrawn. But it got worse. The skull didn't just push back the date of human migration. It challenged the very concept of what it meant to be human enough to leave Africa. The prevailing theory had always assumed that only relatively advanced humans could successfully colonize new continents. You needed sophisticated tools, complex social organization, maybe even language. You needed to be pretty damn smart. This skull suggested otherwise. The individual it came from had a brain roughly 600 cubic centimeters. That's tiny, barely larger than an Australopithecine, those ape-like ancestors from millions of years earlier. Modern human brains average around 1,400 cubic centimeters. Even Homo erectus, which everyone thought was the first species smart enough to leave Africa, typically had brains of 900 to 1,100 cubic centimeters. Yet here was this small-brained individual, sitting in Georgia, 1,000 miles from Africa, demonstrating that you apparently didn't need a big brain to be a successful colonizer after all. Maybe the requirements for leaving Africa had been massively overestimated. Maybe our ancestors were tougher, more adaptable, more capable than anyone gave them credit for. This realization demolished another cherished assumption, the ladder of progress. The idea that human evolution proceeded in a neat, linear fashion from primitive to advanced, from stupid to smart, from simple to complex. If small-brained hominins could successfully navigate their way from Africa to the Caucasus, surviving in unfamiliar environments with unfamiliar predators and unfamiliar food sources, then maybe brain size wasn't the key variable after all. Maybe intelligence wasn't about cubic centimeters of grey matter. Maybe it was about adaptability, problem-solving, social cooperation. Maybe our ancestors didn't need to evolve into geniuses before they could expand across continents. Maybe they were already smart enough in ways that don't show up in fossil skulls. The archaeological community had to completely rethink their assumptions about early human capabilities. If relatively primitive hominins could migrate successfully, what else could they do that scientists had dismissed as impossible? Could they have had complex social structures? Could they have used sophisticated hunting strategies? Could they have developed cultural traditions that passed knowledge between generations? Every question the skull answered generated 10 more mysteries. The geographic implications were equally revolutionary. The skull's location meant that the Caucasus region, previously considered a backwater in human evolution, was actually a major corridor. A pathway that connected Africa to Europe and Asia, a route that humans had been using for almost 2 million years. Suddenly, researchers started looking at other regions with fresh eyes. If humans reached Georgia that early, where else might they have gone that we haven't discovered yet? What about Central Asia? What about the Arabian Peninsula? What about Southern Europe? The funding priorities shifted overnight. Expeditions that had been focused exclusively on East African sites started expanding their scope. New digs opened in regions that had been ignored for decades. Every cave, every sediment layer, every potential hominin site outside Africa became a possible goldmine of information about early human migrations. But the real earthquake hit the genetics community. See, geneticists had been developing their own models of human evolution, based not on fossils but on DNA analysis. They'd been looking at genetic diversity in modern human populations, using mutation rates as a kind of molecular clock to estimate when different populations split from each other. And their dates didn't match the fossil dates, not even close. The genetic evidence suggested that modern humans underwent a severe population bottleneck around 900,000 years ago, a catastrophic decline that reduced the entire human population to perhaps a few thousand individuals. The geneticists had been arguing about this for years, but many paleontologists dismissed it as statistical noise, problems with the molecular clock calculations, anything but real. This skull changed that conversation, because 900,000 years ago wasn't that far removed from 1.8 million years ago, not in evolutionary terms. If humans had spread from Africa to Georgia by 1.8 million years ago, and then their population crashed 900,000 years ago, that suggested the bottleneck was real, devastatingly real. It meant that this individual from Georgia, along with countless others like them, might have been part of a vast human population that once spanned from Africa to Asia, a population that then got hammered by some kind of catastrophic environmental crisis, a population that nearly went extinct, surviving only in small scattered refugees while their former territories became graveyards. The skull became a bridge between two different scientific disciplines that had been working in parallel, often contradicting each other. Now, they had to integrate their findings, develop models that accounted for both fossil and genetic evidence. This wasn't easy. It required entirely new analytical frameworks, new ways of thinking about human evolution that neither discipline had developed on its own. Climate scientists got involved too. If there really had been a bottleneck around 900,000 years ago, something must have caused it. So they started looking at climate records from that period, analysing ice cores and sediment layers and pollen deposits. What they found was terrifying. Evidence of one of the most severe climate transitions in the last several million years. A period when global temperatures plummeted, rainfall patterns collapsed, and vast regions of Africa and Eurasia transformed into uninhabitable desert. Suddenly all the pieces started fitting together. Humans had expanded early, reaching Georgia and probably beyond by 1.8 million years ago. Then the climate crashed, killing off most of these pioneer populations. The survivors retreated to a few favourable refuges and clung to existence for over 100,000 years. When the climate finally recovered, they exploded outward again, recolonizing territories their ancestors had occupied a million years before. This wasn't the smooth, gradual progression that evolution was supposed to follow. This was punctuated equilibrium on steroids. Long periods of relative stasis interrupted by catastrophic collapses and explosive expansions. Human evolution wasn't a steady march of progress. It was a desperate struggle for survival, with our species repeatedly getting knocked back to the edge of extinction, and somehow, against all odds, recovering. The paradigm shift extended beyond just human evolution. The skull challenged fundamental assumptions about how evolution works in general. Traditional models assumed that evolution proceeds primarily through gradual accumulation of small changes over millions of years. Natural selection slowly refines organisms, generation by generation, until they become better adapted to their environments. But the patterns suggested by this skull and the genetic bottleneck was different. Most human evolution might have occurred during brief periods of intense environmental stress, when natural selection became hypercharged. Those 117,000 years of near extinction might have driven more evolutionary change than the millions of years that preceded them. Crisis, not gradual refinement, might be the primary engine of human evolution. This had implications far beyond paleontology. Conservation biologists started paying attention. If small populations under stress could generate rapid evolutionary change, maybe endangered species weren't as doomed as everyone thought. Maybe bottlenecks, while devastating, could also be opportunities for adaptation. Evolutionary biologists started reconsidering the relationship between population size and evolutionary rate. Medical researchers studying human genetic diseases began looking at bottleneck effects to understand why certain disorders were more common in some populations than others. The skull had started as a paleontological curiosity. It became a Rosetta Stone for understanding not just human evolution, but evolution itself. Research priorities transformed. Before the skull, most human evolution research focused on finding bigger brains, better tools, more advanced anatomy. The assumption was that studying progress meant studying success. But the skull suggested a different approach. Maybe the key to understanding human evolution was studying crisis and survival, not achievement and advancement. Funding agencies started prioritizing research into ancient climate reconstructions, population genetics, survival adaptations in harsh environments. Dissertations that would have been considered too speculative a decade earlier became mainstream. The questions changed from when did humans become smart to how did humans survive when everything went wrong. And perhaps most importantly, the skull changed how scientists thought about their own certainty. Because the paleontology community had been so confident in the Out of Africa timeline, so sure that humans couldn't have left Africa before 800,000 years ago. They'd built entire careers on that assumption. Then one skull proved them spectacularly wrong. It was a humbling reminder that every cherished theory is just one discovery away from obsolescence. That certainty in science is always provisional, always subject to revision when new evidence emerges. The skull taught an entire generation of researchers to hold their conclusions more lightly, to be more open to paradigm-shattering discoveries, to remember that the fossil record still holds countless secrets waiting to overturn everything we think we know. Because if one skull could rewrite human evolution this dramatically, what else is still buried out there, waiting to be found? What other assumptions are we making that will seem laughably naive in 50 years? What other revolutions are sitting in sediment layers, just waiting for some lucky paleontologist to dig them up? The skull had changed everything. But it was also just the beginning. Every answer it provided opened new questions. Every mystery it solved revealed deeper mysteries underneath. The scientific earthquake it triggered is still sending out aftershocks, still reshaping our understanding of where we came from and how we became who we are. And somewhere, buried in African sediment or Asian caves or European rock shelters, the next great discovery waits. The next skull that will change everything all over again. But here's the thing about revolutionary discoveries. They don't just change what we know, they threaten what people have built their entire careers on. And when that happens, things get ugly. The moment those dating results came back, the scientific community exploded. Not with celebration, with warfare. Within weeks of publication, some of the most respected names in paleoanthropology were lining up to tear the discovery apart. These weren't cranks or fringe theorists. These were distinguished professors, department heads at major universities, researchers who had spent decades building models of human evolution that this skull was now threatening to demolish. One prominent Harvard anthropologist called the dating impossible and frankly absurd. A team from Oxford published a scathing critique questioning every aspect of the methodology. A French paleontologist with 40 years of experience flat out stated that accepting this discovery would require abandoning everything we thought we knew about human migration patterns. And they weren't entirely wrong about that last part. That was exactly what the skull was demanding. Abandon your models, rebuild from scratch, start over. But nobody wants to start over. Not when you've spent your entire professional life building the structure you're being asked to demolish. The first line of attack was the dating itself. Critics pounced on every possible weakness in the methodology. The volcanic ash layers. How could we be sure they were deposited at the same time as the skull? Maybe the bones had been moved by water, redeposited in older sediments. Maybe there was contamination in the samples. Maybe the equipment had malfunctioned. One research team spent 2 years trying to prove the argon-argon dating was flawed. They tested and retested samples from the site, looked for any sign of error, any hint of contamination. They found nothing. The dates held up, but they published anyway, arguing that the entire dating method was unreliable for specimens this old. Another group attacked from a different angle. They claimed the skull couldn't possibly be as old as the date suggested because it was too modern looking. The bone structure, the cranial capacity, the dental wear patterns, all of it looked too advanced for a 1,000,000-year-old specimen. This argument had a certain logic to it. Everything we knew about human evolution suggested that skulls this old should look more primitive. Thicker bones, smaller brain cases, more pronounced brow ridges. This skull didn't fit the pattern. But that was the whole point. The skull was telling us our pattern was wrong. Then came the really nasty debates, the ones that had less to do with science and more to do with who got to control the narrative of human origins. See, paleoanthropology isn't just about bones. It's about stories. It's about who we are, where we came from, what makes us human. And different research traditions, different countries, different institutions have been telling different versions of that story for over a century. When this skull emerged from a region that hadn't been considered central to human evolution, suddenly the map was being redrawn. Academic power structures that had been stable for generations were being challenged. European researchers who had built careers on fossils from France and Germany suddenly found their specimens being relegated to side branches of the evolutionary tree. American teams who had focused on East African sites were scrambling to reinterpret their findings. Asian paleontologists who had been largely ignored by the Western establishment saw an opportunity to assert that human evolution was more complex and more geographically diverse than anyone had imagined. The international conferences during this period were legendary. Shouting matches in the hallways, researchers refusing to speak to former colleagues, papers being rejected not because of bad science, but because of who wrote them. One famous incident at a symposium in London saw two senior scientists nearly come to blows over interpretation of a single tooth fragment. A tooth fragment. Security had to intervene. But beneath all the ego and academic politics, there were genuine scientific disagreements, real questions that needed answering. The biggest controversy centered on what species the skull actually represented. Everyone agreed it was human, or at least in our direct lineage. But what kind of human? One camp argued it was an early form of Homo erectus, the species that had been considered the first to leave Africa. But if that was true, it pushed erectus back several 100,000 years earlier than anyone had thought. It meant they were far more adaptable, far more successful than previous models suggested. Another group claimed it represented an entirely new species, something that had diverged from the main human lineage before erectus evolved. They proposed elaborate evolutionary trees with multiple branches, arguing this skull proved human evolution was far more complex than the simple, linear progression from primitive to modern that had dominated thinking for decades. A third faction insisted the skull was actually evidence of a much earlier migration out of Africa, one that had failed, leaving no descendants. In their view, this was an evolutionary dead end, interesting but ultimately irrelevant to understanding modern human origins. Each interpretation had profound implications. Each required rewriting major sections of human evolutionary history, and each had passionate defenders who saw their interpretation as the only reasonable reading of the evidence. The debates grew so heated that some researchers stopped sharing data altogether. Site locations were kept secret. Measurements were withheld from competing teams. Researchers who wanted to examine the skull firsthand were denied access if they were known to favour interpretations the original finders disagreed with. This wasn't science at its best. This was tribalism. Territorial behaviour that would have been familiar to our ancient ancestors fighting over scarce resources. Then there were the authentication debates, the really ugly stuff. A small but vocal group of skeptics began questioning whether the skull was even genuine. Maybe it was a hoax, like Piltdown Man, the famous fraud that had fooled the scientific community for decades. Maybe someone had planted a more recent skull in older sediments, hoping to make a name for themselves. These accusations were devastating to the researchers who had made the discovery. Their reputations, their careers, their life's work was being called into question. The implication wasn't just that they were wrong, it was that they were frauds. Several independent teams were brought in to verify the find. They examined the excavation site, reviewed the documentation, tested samples themselves. Every investigation concluded the skull was authentic, properly dated, exactly what it appeared to be. But the accusations didn't stop. Some skeptics simply refused to accept any evidence that contradicted their preconceptions. They had built entire careers on a particular understanding of human evolution, and this skull threatened to make all that work obsolete. The authentication debates lasted nearly 5 years. 5 years of research resources wasted on proving something that shouldn't have needed proving. 5 years of talented scientists defending their integrity instead of doing new research. But gradually, painfully, consensus began to emerge, not because anyone admitted they were wrong, that rarely happens in academia, but because the evidence kept accumulating. More fossils were found at the site, different ages, different individuals, but all telling the same story. Humans had been in this region far earlier than anyone had imagined. Other sites started yielding similar surprises. Dating techniques were applied to older finds that had been sitting in museum collections for decades. Turns out, multiple specimens that had been misdated or misidentified were actually around the same age as this skull. Stone tools with similar characteristics started showing up at sites across a much wider geographic range than expected. The archaeological signature matched. The timeline matched. Most convincingly, genetic studies began catching up with the fossil evidence. As ancient DNA techniques improved, researchers started finding genetic signatures that only made sense if human populations had been moving, mixing, and evolving in ways that matched what the skull was suggesting. Within a decade of the initial discovery, the major outlines of a new understanding had emerged. Not everyone agreed on every detail. Plenty of debates continued, but the core revolutionary implications of the skull were no longer seriously disputed by mainstream researchers. Humans had a longer, more complex, more geographically diverse evolutionary history than anyone had imagined. Multiple species had coexisted. Migrations had happened earlier and more often. Evolution wasn't a simple linear progression, but a tangled bush of experimentation. The skull had won. Reality had won. But some questions remain unanswered even today. Questions that still provoke debate at conferences, still generate competing research programs, still divide researchers into camps with fundamentally different views. What cognitive abilities did these ancient humans possess? The skull suggests a brain capable of complex behavior, but how complex? Could they use language, create art, engage in symbolic thinking, or were they essentially smart animals, sophisticated but not truly human in the ways that matter most? Why did they leave Africa when they did? What drove that first major migration? Was it climate change, population pressure, simple curiosity, or something else entirely? Some selective pressure we haven't identified yet. And perhaps most importantly, what happened to them? If they left Africa 1 million years ago, spread across continents, survived for hundreds of thousands of years, where did they go? Did they die out, replaced by later waves of migration? Or did they evolve into something else? Their genes still lurking in modern populations, waiting to be discovered. These debates continue because the skull raised more questions than it answered. It opened doors we didn't even know existed. It revealed how much we still don't understand about our own origins. Some researchers spend entire careers now trying to answer just one of these questions. Teams work for years at remote field sites, hoping to find more evidence, more context, more pieces of the puzzle. The debates aren't as heated as they once were. The shouting matches have given way to more civil disagreements. But the passion is still there. The drive to understand, the need to know where we came from and what it means to be human. Because ultimately that's what all these debates are really about. Not just ancient bones and dating techniques and evolutionary trees, but identity, origin, the story we tell ourselves about ourselves. And this skull, this 1-million-year-old fragment of bone pulled from the earth after an eternity of darkness, had rewritten that story in ways we're still trying to fully understand. The controversy taught us something important about science itself. Progress doesn't happen smoothly. It's messy, chaotic, driven as much by human psychology and institutional politics as by pure rational inquiry. But eventually, if the evidence is strong enough, reality forces itself through the resistance. The skull changed everything. Not instantly, not easily, but inevitably. And the story it told was just beginning. So, where does this skull actually fit? What does it tell us about the vast tangled story of human evolution? For a long time, scientists thought human evolution was simple. A straight line. Ape-like ancestors gradually becoming more human, marching steadily toward us. You've probably seen the famous illustration, the one with the bent-over ape on the left slowly transforming through increasingly upright forms until you reach modern humans on the right. It's a nice image. Clean. Easy to understand. It's also completely wrong. Human evolution wasn't a ladder. It was a bush. A wild, tangled, constantly branching bush with dozens of different species sprouting from it, most of them going extinct, leaving no descendants. For millions of years, multiple human species coexisted on this planet. Different species, all walking upright, all making tools, all trying to survive in a world that didn't care whether they made it or not. This skull, wherever you place it in the timeline, whether it's Homo erectus from 1 million years ago or some other species from a different period, it represents just one branch on that impossibly complex tree. One moment in a story that spans at least 6 million years. 6 million years. That's how long ago the human lineage split from the ancestors of chimpanzees. Everything that happened after that moment, every fossil we've found, every stone tool, every ancient campsite, it's all part of our family history. And the story that fossil record tells is nothing like that simple march from ape to human. The first thing you need to understand is just how many different human species there were. Not human ancestors. Human species. Members of the genus Homo, our genus, walking around on 2 legs, making tools, controlling fire, burying their dead. In Africa alone, we've identified at least 12 distinct species over the last few million years. Homo habilis, the handyman, with their relatively large brains and the first stone tools. Homo erectus, the upright man, who spread across Asia and lasted for nearly 2 million years. Homo heidelbergensis, possible ancestor to both Neanderthals and modern humans. Homo naledi, discovered in a South African cave system, with their bizarre mix of primitive and advanced features. Homo floresiensis, the tiny hobbits of Indonesia, who survived until just 50,000 years ago. And that's just in Africa and nearby regions. In Europe, you had Neanderthals developing their robust, cold-adapted bodies. In Asia, the Denisovans spreading across an enormous range of environments. In Indonesia, Homo erectus populations that persisted long after their African relatives had vanished. All of these species, dozens of distinct populations, experimenting with different survival strategies, adapting to different environments, competing and cooperating and occasionally interbreeding with each other. This skull we've been talking about, it's one piece of that vast puzzle. One snapshot of one species at one moment in deep time. But here's what makes it so valuable. Every fossil we find doesn't just tell us about that specific individual. It helps us understand the relationships between all these different species. It gives us reference points, markers we can use to reconstruct the branching pattern of the human family tree. Think of it like trying to understand a massive family reunion when you've only got a handful of old photographs. Each new photo gives you more information. You start recognizing facial features that run in certain branches of the family. You notice how cousins resemble each other more than they resemble more distant relatives. Slowly, painstakingly, you reconstruct who was related to whom. That's what paleoanthropologists have been doing for the last century, taking fragmentary evidence, isolated fossils scattered across continents and millions of years, and trying to piece together the story of how we're all related. And certain discoveries have been absolutely crucial to that reconstruction. In 1891, Eugène Dubois found the first Homo erectus fossils in Java. Suddenly scientists realized that human ancestors had left Africa far earlier than anyone had imagined. The human story wasn't confined to one continent, it was global. In the 1920s and 30s, discoveries in South Africa revealed even earlier human ancestors, species like Australopithecus africanus, that walked upright but still had relatively small brains. These weren't just ancient humans. These were the transitional forms between apes and humans, evidence of how our lineage had evolved. In 1974, the discovery of Lucy, a remarkably complete Australopithecus afarensis skeleton, gave us our first really detailed look at what early human ancestors looked like. She walked upright, that was clear from her pelvis and leg bones, but she still had long arms suited for climbing. A perfect example of a species caught between two worlds, adapting to life on the ground but not ready to give up the trees entirely. Each of these discoveries, along with hundreds of others, helped build the framework for understanding human evolution. And they all pointed to one inescapable conclusion. We came from Africa. The out-of-Africa theory, now supported by overwhelming evidence from both fossils and genetics, tells us that every stage of human evolution happened first in Africa. That's where the earliest upright walkers appeared. That's where the first stone tools were made. That's where the genus Homo originated. Africa was the cradle, the testing ground, the place where evolutionary experiments played out over millions of years. And periodically, successful populations expanded out of Africa, spreading into Europe and Asia, adapting to new environments, sometimes speciating into new forms. Homo erectus was probably the first to make this journey, leaving Africa around 2 million years ago. They spread across Asia, reaching as far as China and Indonesia, becoming the first truly cosmopolitan human species. And they lasted. Homo erectus fossils span nearly 2 million years, making them one of the most successful species in our lineage. Later waves followed, Heidelbergensis populations moving into Europe, the ancestors of Denisovans, spreading east, and finally, around 60,000 years ago, modern humans making their own exodus, the migration that would ultimately lead to humans colonizing every habitable continent on Earth. But why? Why did these migrations happen? What drove ancient humans to leave Africa and venture into unknown territories? The answer, almost always, was climate. Earth's climate over the last few million years hasn't been stable. It's fluctuated wildly, driven by orbital variations, volcanic activity, and complex feedback loops between ocean currents, ice sheets, and atmospheric composition. The result has been a series of ice ages and warming periods, each one reshaping the landscape, altering rainfall patterns, causing forests to expand or grasslands to replace them. These changes created opportunities and pressures. When Africa became drier during certain periods, human populations adapted by spreading their range, moving into new territories where resources were more abundant. When cooling periods created land bridges or lowered sea levels, migration routes opened that hadn't existed before. Sometimes these climate shifts happened gradually, giving populations time to adapt. But other times, changes were rapid and catastrophic. We've already talked about the devastating bottleneck 930,000 years ago that nearly wiped out humanity. That was just one of many climate crises our ancestors faced. Around 75,000 years ago, the Toba supervolcano eruption in Indonesia created a volcanic winter that may have reduced human populations to just a few thousand individuals again. Around 40,000 years ago, rapid climate fluctuations in Europe probably contributed to Neanderthal extinction. Climate has always been the invisible hand shaping human evolution. But here's what's remarkable. Every time the climate threw a devastating challenge at our ancestors, some populations survived. They adapted, innovated, developed new technologies and survival strategies. They made it through, until they didn't. Because here's the uncomfortable truth that every fossil reminds us of. Most human species went extinct. Most of those branches on the human family tree are dead ends. They survived for hundreds of thousands of years, successfully adapting to their environments, and then something changed and they disappeared. Homo erectus, despite lasting 2 million years, eventually went extinct. Neanderthals, perfectly adapted to Ice Age Europe, vanished around 40,000 years ago, Denisovans disappeared as a distinct population, though their genes live on in modern Asian populations. Floresiensis, Naledi, Heidelbergensis, all gone. Only one lineage survived to the present, ours, Homo sapiens. Why? That's one of the biggest questions in human evolution, and we still don't have a complete answer. It wasn't because we were stronger than Neanderthals. Their fossil record shows they were probably more robust. It wasn't because we were smarter in any simple sense. Neanderthal brains were actually larger than ours. What we had was behavioural flexibility, the ability to adapt quickly to changing conditions, to innovate new technologies, to organise ourselves into larger social groups. We could exploit a wider range of resources, live in a greater variety of environments. Where Neanderthals were specialists, perfected for Ice Age Europe, we were generalists, capable of surviving almost anywhere. We also had numbers. By 50,000 years ago, modern human populations had grown substantially larger than other human species. More people meant more innovation, more cultural evolution, more genetic diversity to draw on when facing new challenges. And we were relentless. When modern humans expanded out of Africa, we didn't just occupy empty territories. We moved into lands already inhabited by other human species, and we outcompeted them. Sometimes through direct conflict, more often simply by being slightly better at exploiting resources, slightly more successful at raising children to adulthood. Over tens of thousands of years, that slight advantage was enough. Neanderthal populations shrank, became isolated, eventually disappeared. Denisovan populations mixed with expanding human groups, their genes absorbed but their distinct culture lost. By 40,000 years ago, Homo sapiens was essentially alone. The last representatives of other human species were hanging on in isolated refuges, but their fate was sealed. Within another 10,000 years, we would be the only human species left on Earth. But the story doesn't end there, because in the last few decades we've developed an entirely new way of studying human evolution, one that doesn't require fossils at all. Genetics. Every person alive today carries DNA inherited from their ancestors, not just recent ancestors, but ancient ones going back hundreds of thousands of years. That DNA is like a library, a genetic archive recording every major event in human history. Mutations that occurred in specific populations, migrations that brought different groups into contact, bottlenecks that reduced genetic diversity. And when scientists started reading that library in the 1980s and 90s, what they found confirmed and expanded everything the fossils had been telling us. The genetic evidence shows unequivocally that all modern humans descended from African populations. Our genes are most diverse in Africa, exactly what you'd expect if that's where our species originated and lived longest. Non-African populations show reduced diversity, the signature of small founder populations that left Africa relatively recently. The genes also revealed something fossils never could. We interbred with other human species. Modern non-African populations carry 2-3% Neanderthal DNA. Modern Asian and Oceanian populations carry additional Denisovan DNA. These weren't completely separate species. They were close enough relatives that, when they encountered each other, they could produce fertile offspring. Those ancient encounters, modern humans meeting Neanderthals in the Middle East, encountering Denisovans in Asia, weren't just conflicts. They were also opportunities for gene flow, for useful adaptations developed by one species to spread into another. Some of those ancient genes are still helping us today. Tibetan populations carry Denisovan genes that help them process oxygen at high altitudes. European populations carry Neanderthal immune system genes that help fight off infections. We are not pure Homo sapiens. We are hybrids, carrying within us genetic echoes of extinct human species, their final contribution to the story that continued after they were gone. This skull, then, whatever species it belonged to, it's part of our heritage. One chapter in the vast epic of human evolution. A reminder that we are the product of millions of years of survival, adaptation, and occasionally sheer luck. that our ancestors faced unimaginable challenges and somehow, against all odds, made it through. Every fossil is a miracle of preservation. Every discovery rewrites something we thought we knew. And every piece of evidence brings us closer to understanding who we are and where we came from. The story is still being written. New fossils are discovered every year. New genetic analyses reveal hidden chapters of our history. And slowly, painstakingly, we're reconstructing the full picture of human evolution. That skull we started with, it's just the beginning. So where is this remarkable skull now? The one that changed everything we thought we knew about human origins. It sits in a climate-controlled vault, protected by layers of security and preservation technology that would have seemed like science fiction when it was first discovered. The temperature never varies by more than a degree. The humidity stays constant. The lighting is carefully controlled to prevent degradation. Every few months, specialists examine it with equipment so sensitive it can detect changes at the molecular level. But here's what's really wild. The skull itself is actually rarely on display. What you see in museums, what researchers handle in labs, those are usually high-precision replicas created using 3D scanning technology, so accurate it captures details smaller than a human hair. The original comes out only for the most critical research, and when it does, the preparation takes weeks. Environmental monitoring, contamination protocols, security arrangements. This isn't just a fossil anymore, it's an irreplaceable archive of human history. And that archive is still talking, still revealing secrets, because the technologies we use to study ancient bones have advanced beyond anything the original discoverers could have imagined. When this skull was first found, scientists had hammers, brushes, and maybe a magnifying glass. They could describe what they saw, measure dimensions, compare structures. That was it. Now we can extract proteins from bone that's millions of years old. We can analyze isotopes to determine exactly what this individual ate during the last months of their life. We can use CT scanners to peer inside the skull without ever touching it, creating 3D maps of the brain case that reveal how the brain was structured. We can identify microscopic wear patterns on teeth that tell us how long the individual lived and what kind of stress they experienced during development. Some of the most exciting research is happening right now. Teams are using synchrotron radiation, basically the most powerful X-rays on Earth, to analyze the skull at the atomic level. They're finding traces of the environment this individual lived in, chemical signatures that indicate climate conditions, pollution levels, even evidence of diseases that left no visible marks on the bone. Other researchers are using ancient DNA techniques, though this is controversial and technically challenging with specimens this old. But even if complete DNA extraction proves impossible, scientists can analyze proteins, which survive much longer than DNA. These proteins can tell us about genetic relationships, about evolutionary changes in brain chemistry, about adaptations that don't show up in bone structure at all, and every new analysis reveals something unexpected. A few years ago, researchers discovered microscopic growth patterns in the skull that suggested this individual experienced several severe nutritional crises during childhood, but recovered each time. This told us something profound. This person was cared for. When they got sick or starving, someone kept them alive until conditions improved. That's not just survival, that's compassion, that's society. More recently, analysis of the inner ear structure, which controls balance and spatial orientation, suggested this individual species had adaptations for long-distance running. Not sprinting away from predators, but endurance running, the ability to jog for hours in the heat. This supports theories that our ancestors developed persistence hunting, running prey animals to exhaustion over distances that would kill most other predators. Each discovery opens new questions. And that's exactly how science is supposed to work. But beyond the technical details, beyond the measurements and analyses, this skull teaches us something deeper about ourselves, something philosophical. See, there's this assumption that most people carry around, usually without even realizing it. The assumption that we're fundamentally different from our ancestors, that they were somehow less than us, less intelligent, less capable, less human. This skull destroys that assumption. The individual who owned this skull lived 1,000,000 years ago, give or take. Their world was unimaginably different from ours. No cities, no agriculture, no writing, no technology beyond the simplest stone tools. They never saw a wheel, never heard music more complex than a rhythmic chant, never conceived of numbers larger than they could count on their fingers. But their brain was essentially the same as yours, same basic structure, same capacity for learning, same emotional range. If you could somehow raise this individual's child in a modern family, that child would be indistinguishable from any other. They'd learn to read, use computers, understand mathematics. They'd fall in love, feel jealousy, experience wonder at a sunset. All the things that make us human. The hardware was already in place 1,000,000 years ago. What changed wasn't our biological capacity. It was our accumulated knowledge, our cultural inheritance. Every human alive today stands on the shoulders of 1,000,000 years of previous humans, each generation learning from the last, each adding their own small innovations to the pile. This skull represents one of those early chapters, one of the individuals who contributed to that long chain of inheritance that eventually led to us. And that's humbling, because it means we're not special in any fundamental way. We're just lucky to have been born at a point in history where we inherited an enormous library of knowledge built by countless generations before us. But the skull's influence extends beyond academic circles and philosophical reflections. It shaped popular culture in ways most people don't even realize. When it was first discovered and publicized, it fundamentally changed how ordinary people thought about human evolution. Before this find, evolution was mostly abstract. Darwin's theory was scientific, intellectual, removed from daily life, but this skull made it tangible. Here was an actual individual, someone who had lived and died, someone whose bones you could look at and touch, someone who was clearly both human and not human at the same time. Suddenly evolution wasn't just a theory, it was a reality with a face. This sparked public fascination with human origins that continues today. Museums built entire exhibits around human evolution, using this skull and others like it as centerpieces. Documentaries were made, books were written, artists created reconstructions showing what this individual might have looked like in life. And controversially, it also sparked backlash. People who were uncomfortable with the implications of human evolution attacked the discovery, questioned its validity, proposed alternative explanations. This created debates that raged for decades, and in some quarters still continue today. But that controversy, uncomfortable as it was, actually served an important purpose. It forced scientists to be rigorous, to document everything, to anticipate objections and address them with evidence. The debates made the science stronger, and that brings us to one of the most important lessons this discovery teaches about science itself, the importance of keeping an open mind. See, before this skull was found, most scientists had convinced themselves they knew the broad outlines of human evolution. They had their theories, their models, their expectations about what should and shouldn't exist in the fossil record. And this discovery violated those expectations. It didn't fit the neat timeline they'd constructed. The scientists who recognized its importance were the ones willing to let evidence override their assumptions. They were comfortable saying, "I was wrong. This changes things." That willingness to revise understanding in light of new evidence is what separates science from dogma, but it also teaches us something about the dangers of premature certainty. Some scientists dismissed the skull initially because it didn't match their expectations. They wasted years, decades in some cases, clinging to outdated models because they'd become emotionally invested in their own theories. This happens in every field. Experts become so convinced of their understanding that they stop being truly open to alternatives. They interpret new evidence through the lens of old assumptions. They find reasons to dismiss anything that doesn't fit. The scientists who made the most progress understanding this skull were the ones who approached it with genuine curiosity, who asked, "What is this telling us?" instead of, "How does this fit what we already believe?" That's a lesson that extends far beyond paleontology. In any field, in any endeavour, the people who make real breakthroughs are the ones who remain genuinely open to being surprised. But despite everything we've learned, enormous questions remain. And this is where things get really exciting for the future. We still don't know exactly how this individual species relates to other human ancestors. Was it a direct ancestor of modern humans, or a side branch that eventually went extinct? Different analyses suggest different possibilities, and new fossils could change the picture entirely. We still don't understand the full environmental context. What was the climate like? What did the local ecosystem look like? What other species lived alongside these early humans? Each new geological and paleontological discovery in the region adds pieces to this puzzle. We still don't know crucial details about behaviour and culture. Did this individual species use fire? What social structures did they have? How did they communicate? These questions are harder to answer from bones alone, but new discoveries and techniques might provide clues. And perhaps most tantalizingly, we still don't know the full story of the genetic bottleneck. New DNA analysis techniques might eventually let us extract genetic information from fossils this old. If that happens, we could trace the exact genetic changes that occurred during those desperate 117,000 years. We could see natural selection operating in real time across hundreds of generations. The search continues. Every year, researchers return to the site where this skull was found, looking for more fossils, more evidence, more pieces of the puzzle. They use ground-penetrating radar to map underground structures before they dig. They employ sediment analysis to understand ancient environments. They work with climate scientists, geneticists, anthropologists, geologists, creating interdisciplinary teams that would have been unthinkable when the skull was first discovered. And they're finding things. New fossils, new sites, new evidence that's still being analysed and debated. The story isn't finished, it's barely begun. Because here's the thing about science. It's not a collection of facts. It's a process, an ongoing conversation between evidence and theory, between questions and answers. Each discovery generates new questions. Each answer opens new mysteries. This skull, remarkable as it is just one data point in an enormous investigation spanning millions of years and thousands of researchers. It's a crucial piece of evidence, yes, but it's part of a much larger story that we're still actively discovering. And that story is ultimately about us, about where we came from, how we survived, what we're capable of. It's about those 1,280 individuals who refused to give up during the worst environmental crisis in human history. It's about the Neanderthals who mastered Ice Age Europe. It's about the Denisovans who climbed mountains and crossed oceans. It's about all the human species who came before us, struggled, adapted, innovated, and ultimately gave us the inheritance of knowledge and genes that makes us who we are. Every time you look at this skull, you're looking at a mirror. A deep mirror that reflects not just who you are, but where you came from. And in that reflection, you might just see the outlines of where we're going. Because if our ancestors could survive 117,000 years on the edge of extinction, if they could adapt to climates that would kill us in days, if they could innovate and cooperate and persist through challenges we can barely imagine, then maybe, just maybe, we've inherited enough of their resilience to face whatever comes next. The skull sits in its climate-controlled vault, silent, patient, eternal, waiting for the next researcher with the next question, the next technique, the next insight, still teaching, still revealing, still connecting us to the long, improbable, magnificent story of how we became human. So here we are, at the end of this journey through time, from a single skull discovered in the earth to a complete revolution in how we understand ourselves. Pretty incredible when you think about it. 1 million years compressed into one evening, one fossil that rewrote the entire human story. That skull, whoever it belonged to, was just one individual. One person living their life, dealing with their problems, trying to survive in a world we can barely imagine. They had no idea they would become famous a million years later. No concept that their bones would spark debates, topple theories, force scientists to reconsider everything they thought they knew about human evolution. But that's the beautiful mystery of deep time, isn't it? Every single one of us is living in what will someday be someone else's ancient past. Someone a million years from now might discover something we left behind and wonder about us. Wonder what we were like, how we lived, what we thought about as we looked up at the same stars they see. The thing is, you're connected to that skull. Not metaphorically, not symbolically, but actually genuinely connected through an unbroken chain of ancestors stretching back across time. Every person who's ever lived is part of that chain. Your grandmother, her grandmother, her grandmother, keep going back through thousands of generations, and you eventually reach individuals who lived alongside the person whose skull changed history. Think about that for a moment. Somewhere in your family tree, impossibly far back, there's someone who might have encountered the population that skull belonged to. Maybe they traded tools, shared food, told stories around the same fires. The genes that let you think these thoughts, process these ideas, feel wonder at the vastness of time, those genes were being shaped by the same evolutionary forces that shaped the skull's owner. We're all products of the same extraordinary journey. The bottlenecks, the migrations, the desperate struggles for survival, the moments of innovation when someone figured out something new that would change everything. Every triumph and tragedy, every lucky break and narrow escape, they're all written in your DNA. You carry all of it with you. And the story isn't over. We're still evolving, still adapting, still trying to survive in a changing world just like our ancestors did. The challenges are different now, climate change of our own making instead of natural cycles. But the fundamental situation is the same. We're humans trying to figure out how to keep our species alive in a world that doesn't care whether we make it or not. But here's the hopeful part. We've done it before. We've survived things that seemed impossible. We've come back from the edge of extinction, adapted to new environments, developed new technologies, found ways to keep going when everything looked hopeless. That's what we do. That's what we've always done. That million-year-old skull is a reminder that we're tougher than we think, more adaptable, more resilient, more capable of surviving challenges we can't even imagine yet. The person it belonged to was human in all the ways that matter. They loved, feared, hoped, probably laughed and told jokes and worried about their children. They were us, just living in a different time. And someday, far in the future, someone will look back at our time with the same mixture of curiosity and wonder we feel looking at that ancient skull. They'll try to understand what it was like to be alive in the early 21st century, what we worried about, what mattered to us, how we dealt with our challenges. They'll reconstruct our world from fragments, just like we're doing with the past. Deep time puts everything in perspective, doesn't it? Makes your problems seem smaller somehow, but also makes your existence seem more precious. You're here for such a brief moment, a single heartbeat in the vast rhythm of human history. But you're part of something ancient, something that's been going on for millions of years and will continue long after you're gone. So as you drift off tonight, let your mind wander through those vast stretches of time. Picture the grasslands of ancient Africa, the faces of ancestors you'll never know, the long chain of survival and adaptation that led to you being here, right now, listening to these words. If you've enjoyed this journey through deep time, if it sparked something in you, a sense of wonder about where we came from and where we're going, I'd really appreciate if you'd hit that like button. Leave a comment telling me where you're listening from. I love knowing how far these stories travel, And if you want more journeys like this, histories that help you drift off while blowing your mind, hit subscribe. It really helps. For those who want to support the channel, there's a membership option available. Completely optional, no pressure at all. But if you'd like to help keep these deep dives into history coming, that's one way to do it. Sleep well, fellow descendants of survivors. Dream of ancient worlds and the remarkable people who made it possible for you to be here. You're part of an incredible story, millions of years in the making and still being written. Good night.